Hello and welcome back to Calculus 1, section 2.6, continuity. This is our first time when we are going to apply limits in another mathematical setting to explain continuity. After that, we are going to use limits to define derivatives and then also integrals eventually. So, the talk of continuity, you understand what continuity means as a word in the language. In mathematics means the same thing. It is wrong to think that only the functions that you can draw by continuous stroke are continuous, because we can actually cleverly construct functions that you have to draw piece by piece by lifting the pen, and they are continuous. There are also piecewise functions which we draw piece by piece and they are continuous. So it's not the notion that you can just draw the line as much as this notion that there should not be interruptions in a line, there should not be jumps in a line. So something that is continuous will look like that, or it might look like, as I mentioned, a piecewise function. So you have this, maybe parabola afterwards, right? It's still continuous. It's still continuous. Now, non-continuous functions could simply be discontinuous functions could simply be that you see there is a hole in the graph and it's the point of discontinuity, or it could be what we call jump discontinuity, where you work on piecewise functions and then you have this situation happen. So the first two on top are continuous. And the two on the bottom not continuous. There is a very simple statement for continuity at the point, which you learn, and then you use that concept to define global continuity. So we start with continuity at the point. So point is a, f of a, right? Because y is equal to f of a, so that's the y value for the given input. And it goes like this. Function f of x is continuous at x equals a if, and we have these three rules. F of a exists. Number two, limit of f of x as x goes to a exists. And three, limit x goes to a of f of x is equal to f of a. This is the theorem. And these three parts are the calculations that you will be performing to check if the function is continuous at the point. For instance, check for continuity at x equals to 3 for f of x equal x squared minus 1. You will simply go and say f of 3 is 3 squared minus 1, which is 8. So exists, passes that. Number 2, limit of x squared minus 1 as x goes to 3 is also 8. Number 3, 8 equals 8, passes. So because of these three, they all pass, right? So because of that, you would say yes, x squared minus 1 is continuous at x equals 3. I can't say continuous and walk away. It's continuous at 3. We have no clue what's happening at 3.1. We have no clue what's happening at pi. We have no clue what's happening at negative 100. We're only certain about continuity at 3. This theorem is giving us continuity 1 point at a time. So we are going to use this to check single points, right? And we generally use this for piecewise functions to see if the piecewise function is continuous without drawing the graph and struggling with multiple functions and domains and so on. So this was a very quick example to illustrate how this works. We'll obviously do much more. Let's just define the rest of the stuff. So global continuity if the function f of x is continuous at every point x equals a in its domain, then f of x is globally continuous. Now we just call that continuous. So if you say if the function is continuous, you are actually looking for global continuity, not a point one. So global continuity says that if the function is continuous at every point, it's continuous everywhere, which kind of makes sense, right? Can we check this using the point continuity? How many calculations would we have to do to check? Infinitely many, exactly. So it is not a practical way to find the continuity of the entire function by computing a single point at a time. So what do we do instead? Instead, we are going to write the theorem on global continuity of functions, which were proved. And we remember that theorem, and then we quote and cite that theorem and take what we need as we work on problems. So the following functions are continuous on their respective domains. Number one, polynomial. All polynomial function. Constant function is a polynomial, and then linear line is polynomial, quadratic, cubic, quadric, all of them. So all polynomials are continuous on their entire domain. You want to put the domain? Sure. Number two, sine x and cosine x are also globally continuous right? They have no vertical asymptotes, they have no open circles, right? Missing points and so on. Tangent is not. Tangent has infinitely many vertical asymptotes. Tangent is not continuous. So tangent is cut infinitely many times. And so are the other three, cotangent, cosecant, and secant. All of them have infinitely many vertical asymptotes, so none of them are continuous. Sine and cosine are the only two, right, 2 out of 6, well, 1/3 of them, right? Number 3, number 3, exponential function, right? Again, negative infinity to positive infinity. Number 4, logarithmic. This one goes from 0 to infinity. Number 5, radical. Radical function is continuous. That's y equals square root of x. But this one goes 0 to infinity. It includes 0. So following functions are continuous on their respective domains. All of these, I am missing more. Maybe not. For now. Is absolute value function continuous on its domain? You want to say yes. Because if absolute value function is absolute value of x, you're correct. How about absolute value of tangent x? Right? Not so much. So we have to be careful about that. We are going to actually single out y equal absolute x. You're correct. On negative infinity to positive infinity. But we need this to single this one out because of what's coming next. And that is combination of functions. All combinations, including function composition, are preserving continuity. So if you combine two continuous functions, you will get continuous function. That is also a major theorem for this section. So if we combine two continuous functions, the result is a continuous function. This statement includes function composition, which is when you plug one function into another. Very easy to ruin continuity. And I think we did this. We did everything that we needed. Now we're going to go back and explain each one of these concepts and do a lot of examples. Where do we start? First, we start in analyzing what it means for a function to be discontinuous. Discontinuities. Let's take a look. Remember what we had for a point. The function value exists, the limit exists, and they're the same. I'm going to draw 3 graphs and ask you to tell me which rule is the first one to fail. Say I have something like this, something like that, and something like this. So this is A, this is A, this is A. It does not take a nuclear physicist here to see that all three of these are discontinuous, right? I just want to know, out of three rules, which one fails for each one of these pictures. Which rule fails for the first one? Rule number 1, rule number 2, or rule number 3? And why? Yes. Rule number 2. Very good. So for the first one, it passes rule number 1 because function value exists. Right? Number 2 is the one that fails. The limit doesn't exist. If you look at the limit from the left, is this value, the limit to the right is this value, they're not the same value, so no limit. Functional value exists, it's whatever the dot is. So it passes the first rule because it does have functional value that exists, which also matches the left limit, but then limit didn't exist because the right limit was off. Great. So how about the second graph? Which rule fails? Rule number 1, rule number 2, rule number 3? Rule number 1 fails. Very good. Rule number 1 fails immediately because there's no functional value at A anywhere. So you try to compute f of A, it comes up as does not exist because as you draw, right, this infinite line through A, it will never cut the function to bounce off into the y-axis. And by process of elimination, what fails on the last one? Yeah, rule 3. It passes the first one. It has the function value. You see that one, right? It has the function value. It's whatever this number here is, so on y. So that's good. Also passes the limit, because the left limit and the right limit both give us the same value, which is whatever that value number there is, right? So your function value is this point, which is this value, and your limit is left and right. They end up at the same elevation, so that's the limit. So overall limit exists, passes number 2, function value passes number 1, but they are not the same number. So it fails number 3. It fails to have the limit equal to the functional value. So this is how you study this continuity. You look at these cases. These are the only cases you can have for discontinuities. Yeah, well, there's a vertical asymptote as well, but that is, well, when you have vertical asymptote, there's no function values, right? Can't be continuous, because on the vertical asymptote, you can't have y. Yes?
For the first one, it says the first one passes the thing, and the second
fails.
fails. So it means the third one is also going to fail, right?
Yeah, but as soon as one is out.
Okay, so
right?
one is out, the third one is out.
Exactly. As soon as one fails, the rest of them, we don't have to check, right? Because in mathematics, there are no exceptions. There are no gray areas. There are no opinions or feelings. No one is considered. So what happens is, as soon as something doesn't work, the entire thing immediately is out. No exceptions at all. Anywhere. So that's the story on discontinuities, which is related to our continuity at the point definition, because it's one of the 3 rules that it's ruined. Now, if the point passes, right, then we know that it's continuous. Now look at this. Are these functions, so these functions are globally discontinuous. Would we agree on that? We just show which rule fails for each one of these graphs, and we all agree that this is discontinuous, globally discontinuous. But all 3 are piecewise continuous. They're continuous on the portion of the domain. So piecewise continuous meaning, you see, this part over here is continuous. And sometimes that's all you need for the problem. So you don't get to write off the function as globally discontinuous and forget about it. For some cases, in some problems, in some situations, it is enough for you to have a part of that function continuous because your problem might be dealing with only that portion of the graph. The best way for me to show this is to jump into one of these continuity proofs that you guys have to do in Calc 2 every time you're solving, every time you're setting up the problem for integration. Let me just see if I can quickly find, let's try this one. 8 point, this one. All right, so that's divergence test, integral test. Okay, cool. So to do something is called integral test in Calc 2, you have to show, as you can see over here on the list, that the function is continuous. And that's the proof that you have to do to set up the problem, and then you do the problem afterwards. I didn't do the continuity in this problem. I just checked it off because, as you can see, but the important part is, observe my function, 1 over x. What do we know about 1 over x? It has a vertical asymptote. As soon as it has vertical asymptote, it's globally discontinuous, no further talk, right? That's the end of the story. But for our problem, all I need are numbers from 1 to infinity. If you consider the piece of 1 over x graph, 1 to infinity, do you see that it's continuous? So this is the reason why you need the concept of piecewise continuity as well. So we have a point continuity, which is continuity at a single point. That gives rise to the global continuity. If the function is continuous at every point, it's globally continuous. But then, for discontinuous functions, we want to also consider each piece by itself and call each piece by itself piecewise continuous. So 1 over x function has 2 piecewise continuous pieces. Function is globally discontinuous. Function is discontinuous at point 0, right? Fails the first part, right, which is no function value. Also fails the second one, no limit. You see that it's needed for something like this to solve problems later on. So in continuity, we are going to consider also piecewise continuity, and that would be that the one piece is continuous. The next part is dealing with the global continuity. We already mentioned that we are not going to sit for an eternity and compute every single number from negative infinity to prove that it's continuous, right? You have to do 3 calculations each time. We have a theorem which states that the following functions are continuous on their respective domains, and you have polynomial, exponential, logarithmic, square root, and all of those things. Far more interesting, right? That's a list. You have to learn it. That's the part of learning Calculus 1. And then we have this huge result. If we combine 2 continuous functions, the result is continuous function. What do I mean combine? Add them, subtract them, multiply, divide, square, square root, and finally function composition. So now I want to discuss this combination in detail. Combining continuous functions. We already said that when you combine 2 continuous functions, you get the continuous function. So what do we have? We have f plus g is going to be continuous, f minus g is going to be continuous, f times g is going to be continuous, f divided by g, provided that g is different than 0, is going to be continuous, f squared, square root of f, and no, that's it, and AMD, hold on, and f composed with g as well, also known as f of g of x. So all of these work. And this is already starting on that route where you're actually writing essays every time you need to prove continuity. Again, I'm going to jump to this Calculus 2 and take a look at the example of that just by scrolling down. So the first one I just checked off because the continuity was obvious and clear over there. The function is piecewise continuous, and we need 1 to infinity. So that was just this piece that it's highlighted on the graph, right? So not a big deal. 1 over n squared. I wrote the formal proof for continuity, but again, 1 over n squared, not a big deal. Let's find there we go. Look at the function. 1 over x, you see it here? 1 over x times ln squared of x. That's the function. You are supposed to show that that's continuous, and that part is in a setup of a Calculus 2 problem. But this piece here, this thing that you're doing is a Calc 1 problem from 2.6. So how do we solve it? There we go. Writing this paragraph is the solution. And this is, see, this can show on your first exam, if you pick to have first exam, or your final exam. Because this is Calculus 1 problem. And this Calculus 1 problem is later on a little snippet of the Calculus 2 problem, which takes 15 pages to do. As you can see, right? Because finally we're done with setup. This is where we start Calculus 2 problem right there. Observe, all function combinations of continuous functions produce a continuous function. That's me stating the theorem that is in your notes. Functions, as long as denominator, well, this is abbreviation because I didn't say that this is a polynomial which is continuous. I didn't say that ln is continuous with resulting. So this actually should be much longer than this. This is abbreviation. I guess yeah, this one wasn't that great in terms of. Let me see if I can find a better Calc 2 example, because I did this integral and p series. Let's see. Oh, again, check. Easy. Ah, much better. X is a polynomial, therefore continuous. Ln x is continuous. So that's all the theorem, right, from our class today. And then combinations of continuous function, right? Combinations of continuous function is continuous function. X equals 0 is not in the domain, therefore, right, because we are dividing by 0. So that's also excluded in the domain, and you end up with a continuous function. So you consider all of these pieces, right, because you see that x equals 0 and x equals 1 would both produce 0 in the denominator. We have to address both of those in the statement, because you see our domain starts at 2. See it here again, 2 to infinity. So again, on the piecewise by part, the domain 2 to infinity, we were able to show that the function is continuous. Again, it's needed so we can set up the problem and then eventually do the problem. This is doing the Calculus 2 problem here, but this part continuity here is what we do today, what we learned today. Cool. So let's take a look at an example. Show that f of x equal e to the x divided by x squared plus 1 is continuous on set of all real numbers R. So this is something that you have to know how to do if you're planning on signing up for Calc 2. You've seen it, right? So what do? You will state that e to the x is continuous by the theorem. Where's the theorem? I scroll up. Here it is, in purple, right? So e to the x is continuous by the purple theorem. You want to call it the purple theorem? Call it purple theorem. You can't call it purple theorem in Calc 2, but you can call it purple theorem now. So e to the x is continuous by the purple theorem, whatever. You will also say that the polynomial x squared plus 1 is continuous by the purple theorem, because polynomial is also on the list of continuous functions. So x squared plus 1 is continuous on R by the theorem. Further, you have to put that word in. It just makes it cool. Put the word in. Further, comma, combinations of continuous functions produce a continuous function. And the only thing that you have to address is, because it was division, you have to make sure that the denominator is never 0. And in this case, it's never 0. Since x squared plus 1, you can put different than 0, or you can say is never 0. We have that f of x is equal to e to the x over x squared plus 1 is continuous on set of all real numbers. This notation, double bar R, if you have never seen it before, I believe I talked about it, but it's a faster way, right? You put two bars and two vertical bars and draw the R. It's just negative infinity to infinity. It's a much faster notation than writing negative infinity to infinity. So there it is. It's essay, right? You write a paragraph and you're done. So e to the x is continuous by the theorem. X plus 1 is continuous by the theorem. Combination of continuous functions continuous by the theorem. And then because it was division, you make sure that you mention that. I mean, we got lucky, right? If it was x squared minus 1, we're doomed, because the function would have two vertical asymptotes. There will be a vertical asymptote at -1, vertical asymptote at +1. So the function would have two discontinuities. It is not the case, right? This one, x squared plus 1, does not produce any x values that would make 0. Doesn't have a solution when we set it equal to 0. So none of the values from negative infinity to infinity will give us vertical asymptotes, discontinuities, or anything like that. Therefore, the entire function is giving us this thing. Yes?
The e to the x, is that the logarithm function?
No, it's an exponential function, like 2 to the x or 3 to the x.
So if there's something like logarithm, it's just going to be from 0 to infinity?
And also square root. is 0 to infinity.
So then we can prove that case, right? Because it's negative infinity to point infinity.
Well, first of all, you have to understand that the domain of the entire function, right, would be affected by that. So if this function here had a square root or ln, then it would never, the question would never say show continuity on R, because the input domain, right, the entire world that you're considering is not on R, it's on 0 to infinity. So the question would have to say, like if this was the ln x, the question would say show that this function is continuous on 0 to infinity. Because the domain is, remember when we talked about it 2 weeks ago at the introductory lecture, we have the, no, I'm serious. Remember what I was saying? You say, what? I said, no, I'm serious. I'm telling you that the first day we talked about combining domains, and we said that the most restrictive domain of all functions present is the boss for the entire function. So if you have 15 polynomials combined, and they're all negative infinity to positive infinity, and you have some weird function that is only defined from negative 1 to 1, all of those infinities and everything else for 15 polynomials is gone because of the what I call the grandmother effect. Do we talk about that? The grandmother effect? No? No? Well, to understand that better, right? What I said here, if this was a log function, it will be 0 to infinity. And this is a polynomial negative infinity to infinity. So this one has 0 to infinity. Everything has to be 0 to infinity, because you would not be able to plug in negative 7 because of the log and so on. Which is what I say, you're on a train station with your grandma. The train is leaving slowly. The doors are still open. You would have no problem to just catch that train. But right? At which point you have the moral dilemma, right? So, yeah, you can also say that the right chain is as strong as its weakest link, and so all of those concepts in the world fall to the same thing. The domain is going to be the domain of the most restrictive function. Good. Let's see what else might experience here. I would like to work on some of these piecewise functions. I just need to. Oh, first, let's just quickly consider some of these graphs. Look at all the discontinuity, right, that is happening here. So when you open your textbook, this was on page 108. When you open your textbook, consider these problems 11 and 12, stare at them, and then just realize what different types of discontinuities you have from point to point, right? Continuous at 0, right, goes in, there is a function value there. Then you have a discontinuity at 1 is a vertical asymptote. Jump discontinuity at 2. And then this point discontinuity at 3. Continuous at 4, it's a spike. We'll learn that it's not differentiable, but it's continuous, so it's all cool. And then 5, again, there is a point there, so continuous. When there are deeper concepts, when you go into continuity, we already said point continuity, global continuity, piecewise continuity, discontinuity, then jump discontinuity. And there's also an idea of removable versus non-removable discontinuity, which is not discussed in this book, which is, can you fix it? Clearly no, and clearly yes. This one can be fixed, actually, by taking this point and stuffing it up there, right? That's when the bridge is missing a little section. You can't drive over it. You can fix it, and then you can drive, right? So if the bridge is missing a section of the bridge, we can fix that section. So the bridge is discontinuous until you patch that part of the bridge. And when you patch that part of the bridge, you can drive over the bridge, right? So there's also, there's more to the continuity than what we present in the Calculus 1 course. But you need to learn all of what I presented so that you can do that as part B of a setup of a Calculus 2 problem and then go on from there. So don't study for the grade. Don't study for the grade because that's how you academically die. Love this stuff, cherish it, learn it because it's cool, learn it because you can annoy others, right? And they say, what do you know? Let me show you about removable discontinuities. The best argument of all the times. What do you know? I have kids. Oh, really? There's a PhD in that? Nice. I have no clue. So, yeah. First time someone tells you that. What do you know? Let me show you. It's going to be awesome. That's why I don't go anywhere. So, look at these beautiful questions, 17 through 20. They're all piecewise functions. Let's consider one of them, and you can play with the other three for homework. So, which one should I look at? 18 it is. All right. So problem 18, our textbook, page 108. We have a piecewise function. It has x squared minus 4x plus 3 over x minus 3 if x is different than 3. And it has 2 if x is 3. So you're looking at this and you see that the discontinuity, if it's going to happen, it's going to happen at 3. Because all other values are fine. You have the polynomial divided by the polynomial whose problem point is 3. So you see that the issue point could be 3 and nothing else. One more time. You see that the issue point could be 3. You also see from here that the issue point could be 3. Because it says entire domain, this is full, and so if x is not 3, so that's all numbers, all infinity of numbers except 3, right? And it's 2 if it's 3. So technically this whole line is just a black dot, right? That is on 3, 2 on the graph. So we want to consider this, right? We are looking for point discontinuity, and we know that we have to check 3 rules. Rule number 1 says, does f of 3 exist? Does it? Does it? What is it? It's 2. So f of 3 is 2. Perfect. Number 2, how about the limit of x squared minus 4x plus 3 over x minus 3 and x goes to 3? How about that one? Well, this is where you go the left limit, the right limit, and what the overall limit is doing, and then, right? So this one is now, you see how there is a problem within problem. This is going to be your 2.3 to solve this. So we'll try limit x goes to, let's say, 3 minus. We can factor the numerator as x minus 3, x minus 1, divided by x minus 3. These guys cancel. We got 2. Woohoo! Nice. You do the same thing from the right side. It will be the same calculation. And this is happening just because the denominator died. Since these two are the same, we have that the overall limit as x goes to 3 of x squared minus 4x plus 3 over x minus 3 is also 2. So does the limit exist? Yes, the limit exists. It's 2. And then number 3, 2 equals 2, passes that as well. Nice. Function f of x, I don't want to write the whole thing again, is continuous at 2. X equals 2. Sorry, x equals 3. X equals 3 as input. We can go further than this and show that it's globally continuous, because you would say the polynomial, right, is continuous everywhere, and the other polynomial and denominator is continuous everywhere. And we've shown that the problematic point 3 is also continuous right there. So now you have all of the points except 3 continuous. Then you have a separate part which says 3 is continuous as well. That means everything is continuous. So you can state that this function is globally continuous as well. The question is asking only to figure out what's happening at 3, but you can actually prove global continuity out of that. Yes?
So essentially, overall what's happening is the first part of the piecewise function would normally have an open part at 3.
Yes.
But since we have that second part that's at 3 comma 2, that essentially fills it in.
Yes, very good. Yeah. That's like the long bridge with a section missing. You patch that section and you just drive over the whole thing. Very good. All right, let's see this. So consider the function 2x plus 1 over x. So 2x plus 1 over x, everything cubed. What can you claim about continuity or discontinuity or of this function? Anyone? Yes?
Because of the theorem, we can see that the polynomial and the exponential portion of it are continuous. So the combination of them are continuous as long as x isn't 0.
Good. So everything is continuous except at 0. So what should we say for the entire function? Is it continuous or discontinuous? Discontinuous because of 0. Exactly. So yes, polynomial on top, continuous. Polynomial on the bottom, right? X, continuous as well. But because it's in denominator, can't be 0, but in this case it can, right? So we would say polynomials are continuous, exponential is continuous, function composition of continuous functions is continuous. And then because x equals 0 in denominator, right? Could be 0. We have a discontinuous function. At 0. If you flip this and you have x over 2x plus 1, then discontinuity would be at negative 1/2. Right? So just write it out. Polynomials are continuous. And again, we have two of those. Exponential. Oh no, that's not exponential function. That's also a polynomial. It's like x. This is like x cubed. That's also a polynomial. So we have three polynomials over here. 1, 2, and everything. 3. So we have three polynomials. They're all continuous. And then we'll say function composition of continuous functions is continuous since x equals 0 gives vertical asymptote f of x is globally discontinuous. Done. So we have three polynomial pieces. There's a function composition involved as well. And then all together, because the denominator equals 0, the whole thing is discontinuous, and that's the end of the story. We have one more short piece of this lecture called intermediate value theorem, and then we'll go for a break. Ready? Intermediate value theorem. This is one of those. Sneeze, man! Don't hold it up. Sneeze. We'll deal with it. So this is one of those results that we don't necessarily use, but it's the background of a lot of stuff. If you want to solve an equation by subtracting 3 on both sides or dividing 2 on both sides or whatever it is you do, you're actually using this theorem. But we never teach it because it's technically explains why all of these things work the way they do. So the theorem states, suppose f is continuous on, suppose f of x is continuous on closed interval a, b, and capital L is a number strictly between f of a and f of b. Then there exists at least one number c in AB satisfying f of c equals L. Words, 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 words. If you don't stop and don't think about it and don't read it 15 times, they might mean nothing. But luckily, when we draw two graphs, immediately it makes sense. So say this is the graph, f of x. I pick point A and I pick point B. A is going to give us the answer on y-axis, f of A, and B is going to give us the answer, f of B. So it says there is an L in between, somewhere in between. Doesn't have to be here. Let's put it closer to f of A. It doesn't matter. So that's your L. And I say that that L was produced by the C, and that L is f of C. So you see how C is between A and B, because C is in A and B, and L is between these guys. Now, you might look at this and say, obviously, that's common sense. Why would you even waste time drawing something like this? Who cares? Well, as I said, we don't use these things to compute anything, but we use it to explain why solving equation works. Now, everything you see around yourselves was built because we figured out equations. So think about that concept. When you're solving equation, you're generally looking for y equals 0 for the x-intercept, which is also called solution or a root, right? X-intercept. And if you consider a function, which I draw this way now, here's your A, here's your B, then clearly your C is this answer. But look at your f of A and f of B. One is positive, one is negative. Which means that you can exploit that idea to numerically solve any equation under the sun if you want to sit down and punch number in the calculator over and over and over again. You can actually, by employing this method and spending few hours, you can solve any equation to any decimal precision you want. Any decimal precision. So we can try one of the examples and see, how it works. But what you do is you make initial guess for this A and B interval. You compute function values, and then you cut it in half on one way or another, and then keep the positive and negative numbers in. Well, let me draw this. So let's say that's the function, and you pick this region for your A and B as the A and B interval, and you compute f of A and you compute f of B. You see that f of A will be positive, f of B would be negative, and that immediately means that the function had to cross somewhere between A and B. So you pick random. Now, you don't know how the graph looks like. You don't know what it looks like at all. All you know is that that solution will pass somewhere. So what you do is you keep either A or B, and you pick somewhere value C. So now you see that you pick this value, actually let's call it B star. If you call this a B star, you compute f of A, you have a positive value, you compute f of B star, you also get positive value. That means solution is not here. Which means it has to be B star to B, because it was not there. And when you compute B star and B, you see that the B star will be positive and the B will be negative, right, on the Y, meaning that the solution is there. Then you cut again somewhere. You keep cutting, eventually it starts going with the decimals and going to the decimals and going to the decimals. It's a very tedious process, but exploiting this process, you guys can go to any decimal precision to solve equation without actually knowing any algebra or anything like that. Now, obviously, to explain something like this, it takes the concept of continuity, which assumes all of the mathematics you learned so far. So it's kind of pointless to do it. But you can program it. Any computer science majors here? Anyone? So something like this, you can go home today and write a code for it. See if you can figure out the code, because that's what you want to do. You want to write a code that no one wrote before and make money, right? This is going to be your good practice. We don't look for solutions this way. We know algebra. We know how to solve equations. But you can actually go, I believe I actually did this last time I taught Calculus 1. Let me see. Nope. Oh, I did. So I want to solve x squared minus 3 equals 0. That was the equation. X squared minus 3 equals 0. And as you can see, what I did is I guessed that the answer will be somewhere between 1 and 2. I computed at 1 and 2 and found that one answer is negative, one is positive, which means that because the solution crosses 0, that the answer is definitely between these two numbers. Then I replaced 1 with 1.5. I'm cutting the interval in half, and when I computed the endpoints, look what happened. One is negative, one is positive, confirming that the solution is between those two numbers now. So I cut the interval, my guess interval, I cut it in half, and now it's a half a point. Then I said, all right, let me replace 1.5 with 1.7. So now I'm making the, right? I computed both, and I still get the negative and the positive, which means that the result is definitely between 1.7 and 1.2. And then what I did is I said, well, let me try 1.9, right? Because I went from 1 to 1.5, it was good, to 1.7, it was good. So let me try 1.9. You see why I'm trying 1.9? Because if the answer is between 1.9 and 2, then the answer definitely is starting with 1.9, and then I can just work on decimals following, right? So 1.9, but look what happened with the calculation. Both numbers were positive. That means that the answer is not between 1.9 and 2, so that means that the answer must be between 1.7 and 1.9. Well, I choose 1.7, 1.9, and then I make the inference that the answer has to be between 1.7 and 1.8. Compute both of these, and we get good. One is positive, one. I think I stopped. No, I did compute. 1.7 and 1.8, one negative, one positive. That means that the answer is in that interval. But look, 1.7 and 1.8, right? So I know that the answer starts 1.7. So I note that down. And now I'm going to add decimals. This is 1.70, right? 1.80. So now I can go 1.70, 1.75. I would find that to be good, because I know it's the square root of 3 is the answer, so it's 1.72 and so on. But you don't have to know what the answer is. You keep picking these values, and you spend a lot of time. I said hours, yeah. So you spend a lot of time, and as long as you are guessing these ranges to have one number negative, one number positive, that means that your answer, which crosses the x-axis at 0, will be there. So it's interesting method, and you just keep calculating, and you can go to any precision you want. You will always get the precise answer using this method, but as you can see, it takes a very long time to solve it this way. It's much easier to square root both sides, put plus minus, and then be done, right? So that's it. That's our continuity. When you come back, we'll take a look at the precise definition of the limit.